you a few examples of asymptotic notations. Yeah. So let's do some calculation. Yeah. Sometimes we need to do some proofs, yeah, based on the definitions, sometimes we use definitions, sometimes we calculate the limits. Yeah. So these two different methods to compare the orders of growth for different growth functions. Yeah. All right. Part one, examples. Yeah. The first example, yeah, I want to start with a very simple example. Yeah. Show that n plus 2 belongs to big theta of n. This question, very simple, right? Yeah. N plus 2, that's our f function, okay? Yeah. So our f of n equals this n plus 2. So our g of n equals this n. And to answer this question, you have two different ways, right? The first, the limit way. Yeah, because big theta, we can calculate the limit. Our limit way, we have case number 2, we can calculate the limit of these two functions and see if the ratio equals a non-zero constant c. If it is a non-zero constant c, then we know we have this conclusion, big theta conclusion. Yeah. Yeah. All right. Yeah. It's simple. Yeah. So I can write in this way here. Yeah. The limit f of n over g of n, f of n, n plus 2. G of n is n. And we know the limit is 1. Yeah. It's very easy to find the limit is 1. Okay. Yeah. I hope you know, right? Yeah. You know why the limit is 1. Okay. So do you need my explanation? Yeah. Because I feel it's simple, so I do not do further explanation. Okay, good. Yeah. Dakota. Yeah. Right. Yeah. Yeah. Madison. Yeah. Almost. At what point does it not be 1? Yeah. Yeah. Here, the thing is, because the limit we can write separately. All right. So yeah, because when you ask me the limit, so we can write n over n, the first limit, because we use the limit property, 2 over n, n goes to infinity, right? We can write in this way. The first one is 1, the second one is 0. So that's the reason it's 1. Okay? Yeah. Right. Yeah. Yeah. Not 1, right? Yeah. There are many different ways, not 1. Yes. Yeah. Many different ways, not 1. Yeah. Yeah. All right. Yeah. But here, although the limit way is very simple, in order to do some practice using definition, so I like to prove this question using the definition, upper bound, lower bound. This big theta, we need to find upper bound, lower bound, C1, C2, and we also need to find that non-negative integer n0. We need to find these 3 things. In order to use the definition for this big theta notation, we need to find C1 constant, we need to find C2 constant, and we also need to find n0 constant. It's harder than the limit way. Limit way, you do not need to find those constant. You just calculate the limit. If its limit is non-zero constant, then you can make your conclusion. Yeah. All right, so for the definition, yeah, because this is f function n plus 2, now I need to find lower bound and the upper bound. Lower bound is constant multiple of n, upper bound another constant multiple of n. Two different constant multiples of n. Okay, yeah. So let's work on the lower bound first. We know constant multiple of n, one multiple of n. How about that? 1 times n, because we ignore that plus 2, so the value should be smaller. So n less than n plus 2. That's trivial, yeah. But we get one constant, right? Yeah. And when this inequality holds, yeah, we need to know when this inequality holds. When n greater or equal to 0, it's whole. Yeah. Some of you may argue when n is negative, it also holds, right? Yeah, but our problem size cannot be negative. Okay, we only consider non-negative integer n. Yeah, because that corresponds to our problem size. Yeah. All right. So C2 equals 1. Yeah. Then the upper bound, we need to see what constant multiple times a constant multiple of n is greater than n plus 2. Okay. Can we replace 2 by n and make it larger? Because n plus n equals 2n. Yeah. But this inequality only holds when n greater or equal to 2. Yeah. So when n greater or equal to 2, we have n plus 2 less than or equal to 2n. Yeah. We can make that assumption, yeah, because that n0 condition allows us to make this assumption, n greater or equal to 2. Okay, so then we have the upper bound, the constant 2, that's C1. So now you can see we have C1 constant, we have C2 constant, but what is the n0? N0 should make us satisfy both range conditions. Now, these two must be true. Then n0 equals 2. Yeah. When n greater or equal to 2, then n must be greater or equal to n0. Yeah, both true. Yeah, so we found this n0. Okay, so after we find all these 3 constant, we can make our conclusion, our final conclusion. Yeah. All right. So that is, yeah. All right. That is the first example. Yeah. I need to give you the second example. Okay. All right. Yeah. Show this time lower bound, big omega, lower bound. So n cubed belongs to big omega of n squared. Yeah. Yeah. So here we only need to find the lower bound, Yeah. So this is the lower bound, but what is the range? Yeah. Okay. We can easily see when n greater or equal to 0, this inequality must hold. Yeah. So this time C equals 1, n0 equals 0. Because only lower bound, so that's enough. Okay, yeah. So we can make our, after this, we can make our conclusion. Okay, yeah. So that's 2 simple examples. Yeah. All right. Part 2, Example number 3, this time, yeah, big theta, yeah, but we want to find both upper bound and a lower bound. Yeah, a little harder. First, if you use the limit way, then it's much simpler. Yeah, so let me use the limit way first. M plus 2 cubed over n cubed. Okay, yeah. Equals n over m cube. Yeah. Yeah. We take that cube out of the limit based on the limit property. One of the limit properties. So we can do this way. It's legal. Yeah. Then inside the bracket, you can see it's 1. Yeah. 1 cube, that's 1. Okay. So that's simple. Okay. If we are familiar with some basic properties of the limits, then it's very easy. Yeah. Okay. All right. But here we also want to practice the definition way. Yeah. Because here we are working on big theta notation. So we need to find C1, C2, and N0, both lower bound and upper bound, then N0. Yeah. So let's look at the lower bound first. Lower bound should be easy, right? N cube. Yeah. Yeah. Because both n and n plus 2, they are non-negative integers. Non-negative integers. Then you take cube both sides. It's also true, yeah, when n greater or equal to 0. It must be true. Yeah. Then the upper bound, we do similarly. Yeah, here, the upper bound, m plus 2. Yeah, here, yeah, C2. Yeah, m plus 2, we replace m plus 2 by m plus n. Because when n greater or equal to 2, we can do this. When n greater or equal to 2, we can do this. Yeah. So that is 2n. So 2n raised to cube 8n cube. 8n cube. Okay? Yeah. Here, C1 equals 8. C2, 1, and N0, 2. Yeah. So then we can make the conclusion after this. But here, yeah, I like to point out many students, so my previous students, many students, when they work on this question, they use some hard way, some way, so not, pretty hard. So what they do, yeah, so let me show how they work. So they work on this m plus 2 cube directly. They expand this expression. They use that, sum cube of sum, that formula, to expand it. Yeah. So they write n cubed plus 3, so 6n squared plus, yeah, to 18n plus, sorry, not 18, not that, yeah. So 3 times 2, oh yeah, 6n squared. 6, 2 squared, 2, 4, so 12n plus 8. So they expand this n plus 2 expression, cube expression to this polynomial. Now, it's correct, but if you work on this polynomial, is it much harder? Right? If you want to use constant multiple of n cube for the upper bound of less than equal to C1 n cube, that would be pretty hard, right? Think about that. That would be much harder, right? Yeah. So many students did in this way, so not recommended. Okay. Yeah. So do it in this way. Do not expand. Do not expand that n plus 2 cube. Okay. Yeah. Do estimate before you take the cube operation. Okay. Yeah. You replace the expression inside the parenthesis by constant multiple of n first. Then you put cube on it. Yeah. Yeah. If you do this way, much simpler, because I remember once I gave a question like, n plus 3 to the fifth power. I asked them to show it is in big theta of n to the fifth. Then those students who expand, very complicated. How complicated this one is, right? Yes. And after the expansion, you need to find a C1, appropriate C1. That's too hard, right? Yeah. So do not use that expansion way. Yeah, expansion way will make the question too complicated. Yeah. All right. So that's example 2.4. Yeah, this one show that log of n belongs to little o of n. Yeah. Actually, this question, we did a similar one before. And remember, when we learned that L'Hopital's rule example, we did a similar question of this one. Yeah. So here, yeah, remember that discrete variable we need to convert to continuous variable before we can take the limit, right? Yeah. So here, because here we need to work on this little o notation, the only way we can do the limit way. There is no upper bound, lower bound way. Okay, you cannot use upper bound, lower bound way to do little o notation. So you can only use the limit way. Okay, yeah. So we need to calculate this limit. So we change it to continuous variable x first. Okay, yeah. So this limit, we want to apply the L'Hopital's rule. Before we apply it, we need to check if it's an indeterminate form. If it is an indeterminate form. Yeah. No problem. Yeah, here, yeah, assume hidden base a greater than 1. And yeah, here, yeah, I didn't write indeterminate. Actually, it's an infinity over infinity determinate form. Okay, so we check it. Then we can apply the L'Hopital's rule. We take a derivative. The numerator log base a of x. Now, so we can find the formula. Derivative 1 over the constant multiple, that's log, natural log of a, constant multiple of x. Okay. Denominator, its derivative is 1. Yeah. So after simplification, 1 over natural log of a times x. So that constant. 1 over natural log of a, it's a constant. Yeah. So when x goes to infinity, 1 over x, this limit goes to 0. Okay? Yeah. If the limit is 0, Then we go back to the discrete variable. So this is continuous variable. So we can take derivatives. But after we get the limit, we can go back to the discrete variable version. Oh, yeah. So here, so here I quickly jump to the next topic. Yeah, but actually, if I, yeah, let me write one more step. Yeah, because this implies that limit n goes to infinity, log of n over n equals 0. Okay, yeah. So then we have this little O notation. Okay, yeah, so we complete it. Yeah. All right, yeah, let me stop right here and we take 15-minute break.